Greetings, and welcome to another in a series of welding theory courses narrated by me, Bob Bosworth, President and CTO of Elite Welding Solutions. Today we're going to discuss and go through the intricacies of using AC power to weld aluminum. There's a number of different things we need to talk about as we travel through this process. But the first thing I'd like to talk about is how these processes are defined. We've all seen MIG welding and TIG welding, and we have to define a little bit between the two of them. So let's just do some very basics of that. First off, the power sources used for constant current that we use for TIG welding, you can see highlighted in yellow, they're completely different from the other side of the coin where we use constant voltage. These are two different power sources, meaning that they're not interchangeable. You can't go and buy a constant current power source that TIG welds, stick welds, carbon arc gouges, and a few other things, and use it for MIG welding. It's a completely different type of process. So these welding machines would not be suitable for any type of retrofit to switch them over to wire or anything, or wire consumption. Now, we can't talk about the process until we understand the material. The material itself has a lot of challenges. And what I like to do is I like to bring those challenges to light right off the bat. And then we're going to go through, as we go through the process, we're going to understand how the process fixes the problems that we have with aluminum, specifically having the alternating current. And I'm going to define a little bit along the way as to why we constantly use gas tungsten arc welding for the welding of aluminum and welding for more finer things in the world that require a lot more precision with the process. So we're going to talk about aluminum very basically. If this was the very thing that scared you in high school, don't let it bother you. It's not a big deal. This is a periodic table that makes up basically everything on the planet. There's only a few of them I want to talk about for a moment. The first one is, of course, aluminum. Aluminum is an element. It can be broken down to the atom, and it is the basis for the material that we use. Now, materials are no different than like baking a cake. We have a bunch of ingredients that come together and give us a very specific result. So we add things to it to make it weldable, to make it strong, to make it clean. There's a number of different things. Silicate's always our best friend. Silicate, it helps everything so it welds. The silicate that's in some of the alumins we use for 4043 type of aluminum is upwards of 6% silicate. So there's a lot of silicate in it. Silicate is our friend because it deoxidizes and helps materials to flow. That filler material that you're TIG welding with, if you use a TIG welding 4043, which is very common, especially in automotive, has, like I said, almost 6% silicate in it. Now, argon has been identified here because that's on the periodic table in the long list of inert gases. Inert gases will not combine with any other gases to create a new gas. For example, carbon dioxide is a combination of gases. Argon can't be mixed with anything. And this whole row here where it says helium, neon, argon, krypton, xenon, and radon, this whole row are completely inert, meaning they will not mix with anything else, any other gases, to create a new compound in any way. And helium is an option, but it's become a natural resource and it's become extremely expensive. The cylinders of helium that you see at Party City and places like that, they're usually somewhere around $400 for a cylinder now because helium becomes very scarce. Helium is found naturally in oil wells, and the Americans have most of it. Here's a typical issue that you might have with going through the process of welding fabrications. You have different types of materials. This is an example of an engine cradle. This particular engine cradle uses 6061. 6061, as we find over here, we have 5052, and we have 6063. Now, all of these are chosen because we need to understand why. But I want to just take a moment to understand, especially when it comes to do with an engine cradle, as to why we would be concerned with strength and why we're also as concerned with weakness, because this is going to tie into our quality later on. The main thing that makes these devices so important in the crash test performance is their ability to predict the failure. We're trying to get the engine to roll underneath your feet in a front end collision. We're trying to get the engine to take the impact and give your body more of a chance to decelerate. So sometimes we'll use different types of materials in different places to give us a certain amount of strength. Now, this combination of materials we're seeing here, which is a combination of 60-61, 50-52, and 60-63, can all be welded with a 40-43. It's a completely different type of filler rod. Another discussion we'll have later on is never think that the filler material that you're welding with is exactly like the material that you are actually welding. They're very much different and designed to borrow properties from each other when they're welding. So let's go through the pitfalls and all the bad stuff that has to do with welding aluminum, because there's been a lot of stories told and there's a lot of folklore about welding aluminum. So if you haven't done it before, don't worry. If you have done it before, you know what I mean. First things first, the problem with welding aluminum. The first one is the aluminum melts at 1220 degrees Fahrenheit, but your plasma that you're creating is almost 11,000 degrees. So blowing through this and making a big hole is very, very easy. Now, we have an advantage when we're welding with steel for those that have welded with steel before. And the advantage being, we can see when steel or stainless steels are red hot. We can see when you can kind of judge the temperature, a little bit of a cue based on the look. Aluminum does nothing. It just goes bloop, and that's it. It's gone. Now there's a layer that's on top of the welds that I'm going to show everybody. I'll be doing demonstrations if we do a practical side, but there's a layer on the outside that actually builds up, and over time this layer on the outside protects the aluminum. And there's two layers I want to talk about. The layer on the outside is this invisible oxide layer that builds up that retains hydrogen and moisture and all kinds of problems. Here's the thing. The aluminum, as we talked about before, melts at 1220 degrees, but it takes over 3,700 degrees to get the surface hot enough that to remove this oxide layer. You can't scrub it off. If you want work in some plants where they do a lot of this and they have wash stations, they use some type of a friction wash station, something to disturb this layer on the outside to help us to be able to make clean welds, because this layer is bad news for everything we want to do. Now, aluminum and oxygen forms aluminum oxides, which we discussed in point 3. But now we're talking about something different. Now we're talking about your welding technique and how your welding technique can affect the welding to the point where oxides can start to build up in the weld. Gas coverage, shielding gas coverage, which often is determined by the angle of your torch and the things you do. Gas coverage is critical in all aspects of this. You have to make sure that puddle never sees oxygen, because air has 21% oxygen in it, 78% nitrogen, 1% argon. But if you aren't careful with your torch maneuvers, you can actually get an area too hot, you pull away too quickly, and I'm going to show you a whole bunch of pictures later on to go along with that, to kind of illustrate what happens. Because as soon as that puddle ends up getting exposed to the oxygen, it forms aluminum oxide. Now, for those people that understand their way around a shop, there's a grinding disc right here. This is a wheel that you stick on a pedestal grinder. This is the same stuff. They actually take liquefied aluminum, expose it to pure oxygen, and make what they call the vitrified aluminum oxide discs. And it's literally being converted from a very soft ductile material that aluminum is into one of the second hardest substances on this planet. And some people will say, oh, you broke the tungsten off, it fell into the weld and now it's sparking. And no, you just allowed it to be exposed, and that's all to do with your technique. Aluminum expands and contracts. This isn't really a problem of the reprocess welder or the welder, but it is a problem of the process, I should say the sequence of the welding. It's very important that we sequence welding a certain way so we understand when we're welding something out of aluminum, what direction it's going to move as we start to work our way through the welds that have to get done. Sometimes simply the direction, and this is a very common problem in high production automotive type aluminum welding. We have to do it the same way every time because there are tolerances we have to hit, and we are going to affect everything that the toolie guys have set up, and we have to work together to try to keep it consistent. Now, aluminum cuts us a break. I was talking about the temperature before. Oh my God, it melts at 1220 degrees. I could melt it on my kitchen stove ring. I mean, it's so easy to melt, yet this plasma is so hot. But aluminum cuts us a little bit of slack because it's highly conductive. It tries to move heat away as fast as it possibly can. And this type of conductivity, we can see it at home. You can look at your lawnmower at home. If you look at your lawnmower at home, your lawnmower has an aluminum engine block. It's got fins in it. These fins are meant to to drag heat away from the cylinders and to drag heat towards the outside edge. It increases the surface area. Fins increase the surface area, allowing more heat to move through it and more efficiently. So heat input is the most important thing when it comes to aluminum welding, and our key factor in heat input is always going to be amperage. Now, we have a contact tip if it was GMAW, and we have a tungsten in our case because we're doing GTAW, gas tungsten arc welding. Your rate of travel is an important feature in this. The most welding engineers will tell you that probably one of the most important parameters that we have to deal with is the rate of travel or your travel speed. You are in complete control of this when you're TIG welding, especially from a manual point of view, whether you're doing reprocess or whatever. But your rate of travel is going to have a very high influence on the outcome of these welds. This will be part of your training program, teaching you what these travel rates are. Of course, we have gas flow, and we're going to set that up. And we have wire deposition or wire feed speed if it's gas metal. Deposition rate is done, you have a torch in one hand and a piece of filler material in the other. When it comes to TIG welding or gas tungsten arc welding, the same thing. And this is a manual process where you dip the filler material into the puddle. So we have all these things stacked against us when it comes to welding aluminum. So what works for us now? We have to have the correct metallurgy. Now that's going to be, in most cases, decided for you, whether it's a welding procedure specification in a CSA or an AWS certified shop, or whether it's been defined by your welding engineering team in an automotive company. Welding metallurgy needs to be defined before you start. And you don't just grab anything and weld aluminum. Not all aluminums weld with the same types of materials. Another discussion for another time there. You got to have the correct equipment and setup. So, you could have the greatest technique. Technique's the last one. You could have the greatest technique in the world. If your equipment's not set up properly, we're never going to optimize how good you are at something. So, part of every program will be, once we're on the shop floor, we go through the equipment you use, and each thing is defined. Each parameter that you're in control of is defined. And you're further defined what you're never to touch, and that is things that meet a certain criteria and they're set up a certain way for a specific reason, and usually the customer's been informed. So when they come through and do audits and so forth, the expectation is you're using the machine like we told you to use the machine, and no one gets in trouble. Physical technique and control is probably the biggest challenge when it comes to this, because we have to teach a hand what to do about location. We have to teach a hand what to do for the heat control, the current control that's going to be right on the torch. And we have, of course, a piece of filler material in the other hand. So this other hand is going to be deciding when to put that filler material into the puddle. and that takes a little bit of practice. So let's talk a little about the equipment and the hardware. So this is your typical gas tungsten arc welding equipment. Now this is not like yours. This is much more basic. It just shows, it clearly shows we have a shielding gas service. We have some method of control, whether it's through a flow meter or whether it's through a restrict orifice, right? The goal would be in most cases to be somewhere between 25 and 35 cubic feet an hour coming out of the end here. Could get much lower for something we call micro TIG, but normal operations 25 to 35. Remember that the smaller, this is something for the welding engineering team, but the smaller this cone is, the lower the gas needs to be because we never want to create velocity. So we have our control and we have a feed going to it. We have our power source, which in this particular case has a couple of options. We have AC and DC. If we're going to weld AC, as we've defined at the top, we need to be welding on an alternating current. Now, on alternating current, there's polarity on this machine. It's been identified. This side has positive, this side hasn't been identified. But now we know there's polarity. If it's on alternating current, it doesn't really matter. Alternating current is the balance of current, which we'll talk about soon, between two equal points. The positive time, so what happens is the electricity balances between positive and negative and positive and negative and positive and negative. And these balances are specific. When the current is in, when the electricity or the torch is in negative, when the torch is in negative mode, we're getting penetration. When the torch is in positive mode, we're getting cleaning. More to come on that later on. Now, a quick word about the torch. In the torch, you guys will see extra hoses going into your torches. That's because often we use liquid-cooled torches. I'll have a complete review of the equipment you're using and give you some tips and tricks about that when I see it. I have to kind of wait until I'm at your plant, if I'm coming to your plant, because I don't exactly know what you're using until I get there. So physical technique and control. I want to define a little bit, and I like to draw pictures or like to draw something to put in your mind to understand what this process is doing and how we are controlling it. What are we in control of and what aren't we? So the whole thing begins with a pre-flow of argon. Now usually we've got a torch set up in such a way that the pre-flow runs for a few seconds before you start to weld. That means you'll push the pedal or push the finger control or whatever you do to initiate the TIG process, and there'll be a slight pause. This slight pause purges all the air out of the area before the arc is struck, or before the arc is initiated in this case. So we have argon pre-flow that happens for just a few seconds. Now when we first initiate the arc, we're just waiting. We're not adding any material yet. This is where we add material, and this is the preheat. So we're trying to establish a hot area that has, a little bit of a puddle showing before we start adding filler material. Then we once we get that puddle established, we start adding material. We start doing the weld deposition. And this is us dipping. This is a technique that I'll demonstrate, or somebody will demonstrate for you, so you can practice. Now, once we decide deposition is done and it's time to terminate the weld, that we start to bring the current down. Now, this line that's taken us from initiate preheat, weld deposition, and gone down here and been fluctuating, this is you. This is your foot pedal. This is your finger control. This is your control that's making this happen. This is one of the technique controls that you have to learn to control to do aluminum. It's like I say, we have to be careful with aluminum because it will melt very quickly and it will blow away on us. Now, At the end of your welding process, you're going to stop. Every TIG welder, that's anything at all, has a post-flow program. Now, post-flow means the gas continues to run for a little while after the arc is extinguished. This is there for one reason and one reason only, and it has nothing at all to do with protecting the weld at the end. This only has to do with protecting the tungsten. Tungstens get very hot, and one of the properties of tungstens we'll talk about is they get so hot, they stay hot for a long time. It's a property of tungsten to retain heat. So because of that, we need to give it the opportunity to cool off under the blanket of protection that argon gives it, our inert gas, to make sure the oxygen stays away from this tungsten while it's cooling off. So typical 332 tungstens should have about 20 seconds of post-flow on them, and bigger ones should have even more, because we have to give the tungsten an opportunity to cool off under the protection of argon. So we've been through this now as you go through. So the pre-flow section, if you wanted to go through this at another time, so if the pre-flow section of argon gas, so this is everything that happens prior to the welding process. The initial preheat is just to add the filler material, and whatever that current should be, it's got to be in balance with the amount of the thickness of material that we're trying to heat up. Thicker material require greater heat. The weld deposition, this is your opportunity to dip the filler material into the puddle, making sure the puddle is the right size. Fair amount of things we have to do. We have to think about when we're doing this process. And our termination, which is the critical part, where I will show you, or somebody will show you, the correct crater condition that we have to leave to make sure our welds are sound. We can't have crater cracks or anything else going on inside in the weld or the weld zone. So we need to make sure that's addressed as we close the weld. Then our post flow, which again is to protect the tungsten and keep the torch nice and cool. Okay, moving on to filler metals. We've talked a little bit about this already. It's usually solid aluminum. Now, this piece of aluminum, this could be TIG weld. It could be MIG weld. Most companies use 4043 and 5356. These are very common, especially in automotive applications. Whether you're using TIG material or MIG material, it makes no difference. The 4043 is formulated the same way, and it's drawn from the same way. So there's a few other options. In fact, now there's dozens of options for welding 6061 or any type of a structural aluminum. But one important point I want to mention here is, again, this rod, this wire, it is not the same as the material you're welding, and that's a very specific metallurgical mix. I think I'll take this moment to kind of stomp the idea that it's a metallurgical solution. You have to remember that this filler material needs some of that base metal mixed in with it to help it with its strength characteristics. That's why you'll see quality come to you and say, I don't like the penetration on this one. It's not deep enough, because they're addressing specification that says there needs to be 10%, there needs to be a minimum 20%, whatever it happens to be. The alternating current effect. Again, quick word on heat input. But these are the things we have at our control now. So we understand the importance of heat input. I can overheat the material; it'll melt away on me, and we understand if it's too cool, if the weld doesn't penetrate enough, I might not have my strength. It's all getting finicky, but we have a lot of control, and this is what makes aluminum a little bit of a challenge to learn, but an excellent skill. Is your control is your heat input. In your heat input, first one is your current setting, and that's up to you. With TIG welding AC on aluminum, you always have some type of control, whether it be foot pedal or finger control, And this is one of the other things you have to master along with the process. So your current setting. Your travel speed, that's up to you. How fast you travel across depends on what your heat input is, depends on how quickly and efficiently you can dip the filler material into the puddle. And of course, that deposition rate. If you put the filler material in too high, if you build it up too high, if you get the filler material between the plasma and the puddle and chill the puddle in that regard, you can have effects on the heat input. It won't penetrate as high, even though the current might be the same. You got to make sure you're making sure you have good plasma contact with the base metal. Now, there's a cleaning action that goes on, and I mentioned it a little bit before when I talked about the oxide layer. And as we talked about, just a quick refresher back on that, we talked then about this layer on the outside taking a lot more heat to get it clean for welding. And it does take a lot more heat, even thousands of degrees beyond the melting point. Now again, our trick, or the main benefit we have, is aluminum likes to move heat really fast. And when it moves that heat, it helps us to keep the area cool. But of course, it still will burn through. So the alternating current gives us a balance between cleaning and penetration. We talked about that before, and here's a little illustration for you to see. Because you're going to listen to this machine. If you haven't worked with a machine like this before, it's going to have a buzz. It's going to have a very strong buzz. And this buzz is the alternating current bouncing back and forth. These machines will not be set in pulse mode. They'll have other settings on them in most cases to try to balance the difference between the electrode positive and the electrode negative. So we can see over on this side, we have electron flow coming from the bottom up because electrons always flow towards their positive pole. Positive poles up in this case, positive poles down in this case. Now, in this particular case with the electrode positive, this is the side that we clean the material with. And this is the side that we penetrate with. And here's the AC wave that we end up seeing that becomes a part of all that. So once you start to weld, when we get on this side, if the electrode were positive, when we sit on that one side, and once you start to use it, the arc starts up and it actually starts to strip away layers. And that's the best depiction I could give you from like a cartoon point of view for what's going to happen. And these areas in here on the sides are going to be really white. A lot of people believe that has something to do with a deposit or something that's leaving on the weld. It's actually the bare aluminum being stripped right off. So the high frequency that initiates our arc, I'm just putting this in place here just to understand that we're always trying to, when we have to TIG weld, we don't want to touch the surface. Depending on how your machine's set up, I have to look, but we don't want to touch the tungsten to the surface. We want to try avoiding that with something called high frequency start. A lot of machines are set up for touch start, but they're designed for touch start. This is something I'll talk to each individual company about based on what their machines are set up to be used like. So here we have our balances, and here's a little bit about understanding the balance now. So this is it spends time in electrode positive, spends time in electrode negative. This is a balanced wave, and this AC cycle gives us both cleaning and penetration. A lot of equipment, a lot of machines make this run a little bit differently in that it's unbalanced. So when we run this one, we get less time cleaning and more time in penetration, something we might use for thick material. If your machine is has the capability of setting a balanced AC, you need to refer to somebody in your plant as to where that needs to be set. It's not just something that you can go ahead and set, and it's something that you really should not be changing. And that's all in accordance with a welding engineering technologist or somebody like that, or a PEng who understands what that means. What I'm saying is whether something's balanced or unbalanced and what that balance setting is, it's not at the discretion of the welder. Whatever your training is as a welder, that's not the part you do. That's not something you play with. Now, something to do later on, something to understand later on is removing material. Part of your quality control program is going to be removing material with a burr. Now, this is a typical burr we use to remove material. It's made of tungsten carbide and has very special flutes on it that take aluminum and kind of and rip it off the surface without adding anything to the cleaning zone. There is going to be a rule for almost anything that's going to get welded, any aluminum that's going to get welded, and that is no abrasives. I don't care if it says that it's made for welding or for grinding aluminum or not. It's not made for welding aluminum. It's only made for grinding aluminum. They don't make a carbide related disc that has anything to do with removing material in the weld zone. Aluminum's too soft. Materials get buried in it and they will cause porosity throughout the weld. Any type of abrasives are going to give us nothing but trouble. The abrasives have little bits of glue on them for being attached, or the resin gets in there from the closed coat type of buffing pads, and they will, when hot, cause us all kinds of problems. This is the way to do it. We use an aluminum burr. If we have to grind a weld away, this is the way we do it, with some form of a burr. I do want to point out a little safety precaution here. These will jump on you. This is not a one-handed process. This is a shield down process where your arms are covered and everything's sealed up nice and tight, and your face is covered and you've got two hands on the grinder. These ones that have flutes on them will jump. I actually have a couple of stitches personally from one of these, and I thought I had all the precautions in place, but so be it. And it was right through a glove, by the way. So they're sharp, but they do the right job, and you have to take care with them. So there's a few conditions, and we'll talk about this again during quality, but there's a few conditions where you're using this type of a device, and you have to use it to get to the bottom of the problem. So the three conditions are: number one, cracking of the weld or base metal. Now, this is a little bit tricky because if a crack extends outside of the weld zone, that is a scrap part under certain specifications, specifically automotive. If you have a crack that extends outside of that zone, we have specific instructions from the OEMs to make sure we do not put weld in a place where weld is not supposed to be. It's that simple. Now that actually goes for everything, but to do with automotive, but that's a good rule of thumb. So if you have a crack, it has to get cleaned out. Aluminum oxide, you can actually see that there's black in the weld. The technique has been a problem, and probably left some aluminum oxide for us to try to resolve. Now you could have a grossly mislocated weld. I actually have a good example of this coming up where I took one of this particular device, this die grinder, and relocated a weld. I'm going to show you the three-part process. I believe it comes up in the quality program for this aluminum. So you'll see that very soon. And that concludes this program. Thank you very much.